A photovoltaic system consists of PV panels, which produce DC power when exposed to sunlight, and an inverter, which inverts the DC power into AC power that is fed into the utility grid. 3 different inverter topologies are currently used in PV systems: a traditional string inverter system, a microinverter system, and the solar edge solution. The traditional string inverter topology, which is still used in the vast majority of all installations, has a number of significant drawbacks. In traditional systems, panels are wired in a series as a string. Since each panel has a unique power production profile, which is a function of differences in manufacturing variances, installation parameters, and shading patterns, the entire system's output is limited. The traditional system design requires all strings to be at the same length, using the same type of panels, and to be positioned at the same angle towards the sun. Real-life installation constraints result in either wasted roof space or unnecessary duplication of system components. The DC cables which connect the panels to a string carry high voltage as long as the sun is shining. The traditional inverter cannot shut down the panel's DC voltage, and therefore poses serious risks to installers and firefighters. A traditional system cannot track power output, temperature, or any other parameter of a single panel. This makes it impossible to identify specific panel-level problems remotely. In the 90s, another inverter topology was introduced: the microinverter. This topology takes the functionality of the traditional string inverter and scales it down to fit a single panel. By controlling each panel individually, microinverters are able to solve certain challenges of the traditional system. However, microinverters have their own inherent drawbacks. This topology requires each panel to have its own microinverter with full inverter functionality. Therefore, it has significantly higher upfront costs relative to traditional inverter topology. When we started to develop the solar edge solution, we defined 3 goals: to optimize power generation of each panel individually, to use the same installation methods and components used to install traditional inverter systems, and to compete with the cost of such systems. Eventually, we developed a topology that meets all of these goals. The Solar Edge DC Optimized Inverter topology combines the best of both worlds. Our solution splits the traditional inverter functionality into 2 products: the Power Optimizer and a Simplified Inverter. The Power Optimizers are located on each panel, turning the panels into intelligent panels. These power optimizers provide panel-level tracking and real-time adjustments of current and voltage to the optimal working point of each individual panel. The simplified inverter is installed similarly to a traditional inverter, but it is only responsible for DC-AC inversion and grid connection. Our solution includes 2 additional features: a panel-level cloud-based monitoring platform, which is accessible from any computer or handheld device, and an enhanced safety mechanism. When installers install the Solar Edge solution, they use the same cables, connectors, and methods as used in traditional systems, and are able to install more panels, to combine long strings with short strings, and to install panels on different facets of the roof. The Solar Edge cloud-based monitoring platform provides full data at the panel, string, inverter, and system level. This allows for immediate fault detection, real-time alerts, and comprehensive analysis. These important features reduce operation and maintenance costs. In addition, we have incorporated panel-level safety mechanisms to protect installers, electricians, and firefighters. With the Solar Edge solution, whenever AC power is off, the string's DC high voltage is automatically reduced to a safe voltage. This solution meets new safety regulations in all significant PV markets around the world, as well as the 2014 National Electric Code in the U.S.